This is the video for SLO5, Measures of Position, which corresponds to section 3.3 of the book. We learned about measures of center, mean and median. We learned about measures of spread, standard deviation. And now we're going to put it all together in a certain sense to get a measure of position and discuss what that exactly means. Here's a good guiding example for the importance of this. Look at question 1. We had one player with a certain batting average of 406. Another player in another year, another era of baseball had a batting average of 388. Who had the better batting average? Well, you'd clearly suggest, just based on this, that Ted Williams had a better year, batting average-wise, than Rod Carew, right? 406 is greater than, not 377, 388. Right? But what are the drawbacks to this method? Well, if you know anything about baseball or just sports or just comparisons in general, you could say that players played in different eras. So, raw scores like this don't compare players to their peers. So let's measure how they did relative to their peers. Consider how far above the mean they did, right? I was going to say average, but I don't want to confuse this with average and batting average, right? So it turns out you can go to Fangraphs, you can get the data for this, you can crunch the numbers. It turns out that in 1941, the mean batting average was 280. And in 1977, the mean batting average was 277. Okay? So would that change our minds? Well, let's see. For Ted Williams, compared to his peers, 406 minus 280 equals 126. And for Rod Carew, 388 minus 277 equals 111. So Williams is still better. Whoops, is still better. What are the drawbacks of this method? Well, it takes into account only the center, not the spread. Now, it is true that a lot of times people do care only about the center, or they care too much about the center. This is especially true in sports, but I would say even in just any time you measure things. But what if we did want to take the spread into account? So let's consider the standard deviation. And what we're going to do, if I mention something called the normal distribution, if I ever mention this, I'm going to write it like this. So I'm going to write it with like that, where mu is the mean, sigma is the standard deviation. If we use sample data, I'll write it like this. Okay. Anyway, the z-score, very important measure here, of a data point in a normal distribution is the number of standard deviations that x is from the mean. So this is a formula that we definitely should know. Z equals x minus the mean all over the standard deviation, right? That's literally just the difference. It's like what we did before, right? The score minus the average, but then divided by the standard deviation so that our units are standard deviations, right? And again, if we're doing sample data, then you'd see it written like this, okay? Now, we showed actually last time that batting averages were approximately normally distributed, right? It was the bell curve. So it's okay to talk about z-scores. Now, I went ahead and crunched the numbers. Turns out that the mean and standard deviation 1941 were 280 and 0.033, and 1977 there were 277 and 0.027. Let's see if this changes our answer, right? So for Ted Williams, right, maybe I'll say, actually I'll write it like this. All right, I guess I will do that. I'll write it as Ted Williams has z-score z equals 406 minus 280 all over 0.033. And let's just crunch that number really quickly. So we know that was 126, right? The 406 minus 280 divided by 0.033. Good for a 3.82 z-score, which we'll see later is absolutely fantastic. Right? Over almost 4 standard deviations above the mean, right? That's absurd. Let's see what Rod Carew has. So this is going to be 388 minus 277, right? That was the mean. And then this is going to be divided by the z-score of 0.027, right? Now remember, we know that that's 111 over 0.027. So let me just count for that, right? So we're going to have here 111 divided by 0.027. And look at that. We actually have a 4.11 z-score, somehow higher. So Carew is better here. Once we take spread into account, we have a more full picture of the leagues back then, right? Looks like good hitting was really, really hard to come by in 1977. So Carew actually is better than Ted Williams when you take z-score into account, right? Mean and standard deviation, right? Now, one thing that we can do is the nice thing about z-scores, one of the many nice things, is that you can transform a raw score, like a batting average of 406 or 388, into its z-score. In fact, you can do that with every data point on a distribution. And it'll change the values, but it won't actually change the shape. And just to show you this, let me get out Desmos really quickly and show you. I've used this picture before, right, when talking about normal distributions, right? This is just a graph where the mean here is, 2.8 or whatever, right? The standard deviation can vary, etc. Well, it turns out if you were to convert these to their z-scores, you would be shifting the graph over. The mean z-score is 0. And then you could also make the standard deviation 1. But you see how it's still a normal curve, right? It's still normally distributed. And if you adjusted the range of this graph, right, you just wanted to make it look a little, make the y-axis, for example, go from like negative 0.5 to, 1 or something, it looks just the same as before, right? So this converting raw scores to z-scores doesn't change the overall shape of the curve. So in fact, let me just take that picture, crop it really quickly, and just stick it into our notes here. So let me just write here, changing a raw score, or maybe I'll say, I should say, changing all raw scores of a normal distribution shifts the mean and the standard deviation, but the shape of the curve is the same. All right, so here's an example. I pulled this from the book. The mean length of a 1-year-old spotted flounder is 126, standard deviation 18. 2-year-old, 162 with 28. So one nice thing about z-scores is they can compare different things with different measures, different athletes in different sports, different athletes in the same sport in different years. Harry catches a 147 millimeter 1-year-old. Sally catches a 200 millimeter 2-year-old. Which is more impressive using length relative to age, in other words, using z-score. So let's take a look at this, right? So the z-score for Harry, I'll just call him H. Z-score, yeah, I'll say Harry. Z-score for Harry is going to equal 147 minus 126, right? Because he caught a 1-year-old. And then the standard deviation is 18. Right? And we'll find out what that equals. And on the other hand, the z-score for Sally is 200 minus 162 over 28. So whichever one of those is higher is the more impressive total, right? Because that's how many standard deviations above the mean their catches are, right? So the more standard deviations above the mean, the more impressive. All right, so let's see what we've got here. Parentheses, make sure to put those parentheses there. 147 minus 126, close the parentheses, divided by 18. 1.17. Typically, we round z-scores to the nearest hundredth. That's what we tend to do in statistics class, okay? All right. Now, for the next one, we have 200 minus 162 divided by 28. Ooh, it's close, but it looks like Sally's catch is a little more impressive. 1.36. So Sally's catch is more impressive, right? Because her z-score was higher than his. Okay, now for number 2, Dave claims he caught a fish that had z-score negative 1.2. How long was it? Now, I don't know how someone would know the z-score, but not the length. But suppose it somehow happens. Right, he knows, well, I just know it's 1.2 standard deviations below the mean. Well, let's note that if z equals x minus mu over sigma, then solving for x gives, and this is just basic algebra right here, right? We're going to multiply sigma over and then add mu, and we're going to get x equals mu plus z times sigma. Let me shift that down a little bit. Right there, okay? So, Dave's fish has length x equals, okay, and then it's the mu. Now let's see. Oh, I didn't specify. Let's say a 1-year-old. Suppose it's a 1-year-old, right? Okay. So then the mean is going to be 126 plus negative 1.2 times 18. So let's see what that gives us. 126 minus 1.2 times 18. 104.4 inches. Or millimeters, sorry. 104.4 millimeters. Right, did I get that right? Yeah, 104.4 millimeters, okay. Okay, got that right. All right, now we have similar ways of measuring the data spread in the context of the median. Now remember, median is purely positional, right? It's the literal middle index of the data. So the way that we do this, we don't talk about standard deviation. We divide the data into quartiles. And you can think of these guys as, just fourths, I guess, right? The range of a data set is, and I should say the difference between, or the difference of, its maximum and minimum values. The what we call the interquartile range, which is abbreviated IQR, is the difference between the values Q3 and Q1. The median is labeled Q2. So this is what I mean. If we take a data set, I'll do this over here. If this is the absolute minimum right here, this is the maximum value, then you divide the data into fourths, just like that, right? 1, 2, 3, and 4, right? So what you say here is that this point right here is Q1, that value. This value right here is Q2. It's also the median. And then this value right here is Q3. I guess I'm not sure I've ever heard the max. Max maybe you could be considered as Q4. The min is Q0, but I've never really heard that term. Okay, but that's what we're talking about. Now, this is the procedure that Navidi and Monk give for finding the quartiles. I think is it this guy? Yeah, it's right here. I'm just gonna put it right here, right? Because it's a little technical, but the basic gist is that the first quartile is the first 25% of the data. So you should expect to, multiply the number of data points, right, or multiply n, right, by 0.25, and that's what's going to give it to you, okay? Similar thing for the third quartile, right? So you just pause the video, take a look at this. Note step 3, right, it's a little bit technical right there. All right. Now, the 5-number summary of a data set is the set minimum, Q1, median, which of course is Q2, Q3, and the maximum. Okay? 5 numbers, and they beautifully summarize the data, right? Because they just partition it every 25%, right? So anyway, let's use Minitab to find the 5-number summary for the batting average of qualified MLB hitters, right? And we already have this data out here. Just to let you know, I don't know exactly why this happens, but Minitab finds quartiles a little bit differently from the way the book does it. So we might want to check by hand. We can do that separately. But anyway, if we go to Stat, Basic Stats, Display Descriptive Statistics, we're going to choose C14, Batting Average. And now if we go to Statistics, we're interested in, look, first quartile, median, third quartile, minimum, and the maximum. So let's keep those guys checked and uncheck everything else, and then we get our 5-number summary. So there you go. That's our 5-number summary. Now again, if you check that by hand, you might get something a little bit different. We, of course, will keep this in mind when giving you assessments, that Minitab might give you a slightly different answer. But that's what we get. Now, let's see if we can create a box plot. If we can create a box plot of the data. And then the question is, what do the boxes and whiskers represents? Let's see what we can do, right? Even if we haven't defined a box plot yet, graph. And we go to box plot down there. Just keep it simple. You know which variable we're using. For options, yeah, I think we're okay with this. Let's see. Yep, perfect. Box plot of batting average. Now they do it vertically. I'm used to seeing it horizontal, and that's what the book does too. So we'll probably do ours horizontally for the most part. Honestly, I don't really care which way you do it, but just to let you know, Minitab does it vertically. So there's that. Okay. So what do the boxes and whiskers represent? Well, if you take a look right there, that's the median, which of course equals Q2. This right there is Q1. That right there is Q3. And then what do you think these guys are? Yep, that's right. They are outliers. Now, we haven't formally defined them other to say that they're far away from the center. Okay. But one thing you can do is find the range and the IQR of the data. I'm going to leave that to you. Right? And that shouldn't be very hard, right? Because we have the 5-number summary. Okay. All right, let's move on. Now, before we formally define a box plot, we define an outlier. So now we are actually formally defining an outlier. Now, it's going to be, as you might expect, far to the left or right of the data set, and in particular, far to the left or right of the center measure, right? And more specifically, an outlier is a data point less than, okay, so what we do here is we're going to consider it's got to be less than Q1 minus 1.5 times the IQR, right? Which is Q1 minus 1.5 times Q3 minus Q1, right? Or greater than Q3 plus 1.5 times the IQR, right? Which equals Q3 plus 1.5 times Q3 minus Q1, right? That's what the IQR is, okay? So that's an actual formula for the outlier. So in this section, if I ask you what the outliers are, you can't just use the eye test. You have to do this math out, okay? A box plot is a graph that illustrates the 5-number summary. Make that a little nicer. As well as outliers. So here's how you do it. So to create a box plot, you can look in the book. It's got 6 points. I'm going to just try to replicate that. Find the 5-number summary. Of the data. Then what you're going to do is you're going to draw a short vertical line over the values Q1, Q2, which is the median, and Q3 on a number line. Right, again, they kind of inverted it, right? Theirs was a vertical number line, right? But ours is going to be horizontal. then connect the Q1 and Q3 lines with horizontal lines to make a box, right, containing the Q2 line, right? And then I'd say, find the outliers. Or I guess I'd say find the values. I think they call these the upper and lower limits, right? Q1 minus 1.5 IQR and Q3 plus 1.5 times the IQR, right? And then you're going to draw horizontal lines from the box to, and it's going to be I'm going to be a little vague here, the data points, I guess I should say the last data points before these values. Or I should say maybe not before, but within these values. And then last but not least, draw asterisks for the outliers. Whew. All right, there you go. So that's how to do it. And again, that is what Minitab is doing. So one little exercise you can do is you can try creating the box plot for the Fangraphs data by hand, right? Use this data right here to create your own box plot. Okay. Now, last but not least, a finer way to portion the data is percentiles, right? The nth percentile is the data strictly less than n% of the data and greater than the remaining 100 minus n%. So for example, Kevin scored in the 97th percentile on his MCATs. Good job, Kevin. What percent of students received a higher score? Well, 100 minus 97 equals 3. So 3% scored higher. What scored? There we go. So then looking at the batting average data, what average is roughly in the 71st percentile? Now what I'm going to do, I'm going to put the procedure for computing the data corresponding to a given percentile right here. Okay? And I'm just going to say, try it. And then list the percentiles of Q1 through Q4. If you think about it, right, Q4 is the max of a data set. Right, I think that should make sense. So 100th percentile, that's not exactly a thing. We really say 99th percentile. That's just kind of how it is, right? Because you're better than 99% of the data. You're never better than 100%, right? That would include yourself. But what if the data points weren't quite so nice? Well, I'm going to put this right here. That's the book's procedure for computing the percentile corresponding to the given data value. And that's what we've got for today. Thanks.